We continue our discussion on the complexity of algorithms with an example. So you see here an algorithm, pseudocode for an algorithm called Who Knows? And the first question to you is take a look at it, take it in, and try to figure out what does this algorithm do? You have here as input an array of n integers, and you're initializing a variable who knows to 0. And after that, we have two for loops, two nested for loops. The loop counter variable for the outer for loop is I, and it goes from 1 to n minus 1. And for the inner for loop, we have a loop counter variable j, which goes from whatever I is plus 1 all the way to n. And inside the inner for loop, we have an if condition, which compares the difference between ai and aj, the absolute value of them, and compares that absolute value with who knows. And if that difference between ai and aj is greater than whatever's in who knows, then we update the value of who knows with the new difference. So by the time we get to the end of this algorithm, what do we have? What will we have in the who knows variable? And whenever you see nested for loops, this time iterating over a space in both dimensions, the size equal to the length of the input array A, you can basically think of it as a two-dimensional space. There are some cases that will go through, some cases that we're not going through in these two nested for loops. And the ones that we do access, the ones that we do go through, are the ones that you see colored in blue in this two-dimensional square, in the square of smaller squares. Well, so each side over here is of length n. So basically, one dimension representing I, the other one j. Numbering starts at 1, ends at n on both axes. And so the blue colored squares are basically the cases that these two nested for loops actually go through. So we're not going through the elements on the diagonal. So we're basically not comparing any of the elements in array A with themselves. And see, the thing that we're doing is we're computing the difference between different elements of this array. So of course, the difference of an element with itself is always 0. That's why we're skipping this diagonal. And why are we skipping all these other white elements over here? We're skipping them because they're identical to the ones that we have on the other side, the blue side. The difference between AI and another element AJ is the same as the absolute difference between AJ and AI. So there's really no need to do the labor twice. So once again, if that's what's happening, if who knows is the difference between two elements of array A, and anytime we encounter a pair of values from array A that have a difference larger than what's already in who knows, we update the value of who knows with that new difference variable. So by the time we get to the end of the algorithm, basically what will have happened is who knows will contain the maximum difference between any two numbers in the input sequence A. So This is how many comparisons will basically happen. In the first row over here, you have n minus 1 comparisons happening. That's as many as you have blue boxes in the first row. Then in the next row, when I goes to 2, we go through one less than that comparisons. So n minus 2 comparisons. And then only n minus 3 comparisons until we get to only one comparison on the n minus 1th line. You can add up these numbers of comparisons in each of the outer loops. This is a sequence, one I think you should recognize, and we know that the sum of the sequence is n times n minus 1 divided by 2, which you can expand, and you get 0.5 n squared minus 0.5 n, which means since n squared is the highest order term here, the time complexity of this algorithm is big O of n squared. Here's another algorithm that basically solves the same problem. We've got over here a variable called min, which is initialized to the first element. We've got a variable called max, which is also initialized to the first element in the array. And then we have a for loop, and notice it's a single for loop. And inside of that for loop, in that for loop going from 2 to n, what we do is if ai, I being the counter variable, the loop counter variable, if ai is less than the previously held minimum, we update the value of min. If ai is greater than the currently or up to this point seen largest value held in max, then update the value of max. By the time you come out of the for loop, min will contain the smallest value seen in this array. Max will contain the largest value of this array A. And all we then need to do is compute the difference between max and min, and that is the maximum difference between any two numbers in this input sequence, in this input array of size n. So we have one, we've got one comparison happening over here, we've got another comparison happening over here. And how many times, so that's 2 times inside the loop. And if you want to count the comparisons for the loop as well, I think they should do that. They usually do that. If you want to do that as well, maybe 3 comparisons per iteration. So something like 3n 3n minus 1. So that's one answer. That I think that's what the answer should be. But for some reason, then for the for loop over here, they're not counting the loop counter comparisons happening, and so that brings the number of comparisons down to 2n minus 2. Okay, the time complexity of this algorithm, any way you look at it, any way you count the number of comparisons, the highest order term is a linear term, which means that the time complexity of this algorithm is big O of n. Now, we are from last class familiar with the big O notation. Adjacent in concept to the big O notation is the big theta notation. You remember one problem, one issue with the big O notation was that there are many functions that can be big O of a specific function. So if you recall, the big theta notation is basically a tighter bound, an upper and lower bound on the rate of growth of a function. And I'll begin by showing you a graphic for that. So an image for that, a plot actually. So we have over here a function f, and you can see that initially it travels around quite a bit, but then after a certain point for the independent variable n, at some point after a certain point n0, what happens is that this function remains in the space between function g of n multiplied by some factor c1 and function g of n, the same function g of n, but multiplied by a different larger factor, c2. So basically, in big O, in that case, we say that the function f of n is big theta of g of n. What happens here is that the function g of n is both an upper and lower bound on the rate of growth of function f. Recall that in a previous example that we saw in the last lecture, we had a function that was big O of n square, but what that also meant was that any higher order function such as n cubed, n to the power 4, n to the power 5, 2 to the power n, n factorial, all of these functions, that function is also big O of all of these functions. Now what happens when you specify a function as a big theta function? You're specifying not just an upper bound, but an upper and a lower bound. So it's a more precise, it's a more accurate, still a true statement, but it gives you a narrower bound of range of values within which function f exists after a certain point n0. So, for example, we have a function f that is this 10n squared minus 3n. We can say that it is big theta of n squared. So g of n is an asymptotically tight bound for function f. And since we're talking about big theta, and you already know about big O, guess what? There's another type of bound called a big omega function. And as you might probably be able to guess, the big O function is an upper bound on the rate of growth of a function. Big theta is an upper and lower bound on the rate of growth of a function. And so the big omega function is a lower bound on the rate of growth of a function. So here in the figure on the right, we have function f, which goes on over here. And after a certain point, again, a certain point on the n axis, the independent variable, after a certain point, that function f stays above another function, g of n, which you're allowed to multiply, for which you're allowed to select a factor c. So a big, and the syntax is very similar to what you've seen for the big omega and the big theta functions. We say that, in that case, we say that function f is big omega of function g of n. Now, many functions can be big omega of a function, just like many functions can be big O of a certain function. The intersection of these two sets of functions is what is the big theta function. This is well worth remembering. So some problems are called intractable, or are hard because as the problem sizes grow larger, we are unable to solve these problems within a reasonable time. And what does reasonable time mean? Means polynomial time, meaning n to the power something, n to the power 5, n to the power 3, n to the power 2. So something that when implemented in the form of a program would basically mean nested loops. Okay, if you can do it with any number of nested loops, you have basically and that's the highest order term in the number in the number of operations that you have to perform. You have you have a solution to your problem that is polynomial time. So polynomial time means n square is polynomial time n cube, or anything less than that actually. So anything that's constant complexity, big O of 1, or anything that's big O of n log n, for example. Complexity levels that are not considered polynomial time is anything higher than that, meaning 2 to the power n, big O of n to the power log n. I know we haven't seen this one yet, or worst of all, perhaps, out of what we've seen, big O of n factorial. These are not polynomial time. These are okay. Problems of this, with solutions of this order, are considered tractable. Others are considered intractable. For optimization problems, each feasible solution has an objective value. The goal is to find a feasible solution that optimizes, meaning minimizes or maximizes certain objectives. So consider an optimization problem. Given that you have a weighted graph G, find a Hamiltonian cycle with a minimum weight. Now, there's a whole chapter on graphs that we'll get to. I think it's chapter 10 in our textbook that we'll get to. So this is just one brief mention of an example. So decision problem is a given G and an integer k. Does G have a Hamiltonian cycle with cost k? That is a decision problem. So this is an optimization problem. This is a decision problem. And for a decision problem, shortest path given, so your graph G and two nodes U and V, source and destination, find path from U to V with minimum distance. That's the shortest path problem. Decision problems are easier, or are no harder than corresponding optimization problems. Problems of class P is short for polynomial time, are the ones that can be solved, tractable. Problems of class NP standing for non-deterministic polynomial time, are problems that cannot be solved in polynomial time. So for algorithms people, NP usually refers to classes of to a class of problems that can be verified by a polynomial time algorithm. And that's the end of chapter 3 on algorithms. And next time we'll pick it up from chapter 4.